This is the Supermicro 222H-TN, and it is launching today. Well, okay, it's not launching today. This is actually a chassis the Supermicro's had for a while, but the CPUs in this, these are Xeon 6 6787P, and these just launched on February 24th. But this is a system you can actually buy now. This system is headed for the data center. It's headed for real workloads. Somebody bought this? Yeah, actually. Let's dive in and take a look at the chassis, run some benchmarks, and see some workloads. Okay, first up, Xeon 6, it's simplified, but also not simplified. Intel's doing something that is very good and very awesome, and like I say, the Xeon 6 family of CPUs from Intel are the best CPUs that they've had in 10 years, bar none. These are performance cores. Just like Intel has performance and efficiency cores, performance and efficiency core based Xeons are available in two different socket configurations. So this, the efficiency core, this is the 6780E, that we reviewed, oh gosh, 9 months ago? 9 months ago. This is the exact same socket as the 6787P CPUs that are in here. There's two of them, there's a pair. These are 86 cores. This is 144 cores, if I remember correctly. It's a ton of efficiency cores, but these are performance cores. Performance cores have more features. You got AMX here, you got accelerators. There's all kinds of hardware under the hood. This is the best of the best core. These are about packing them in like sardines, whether that's micro virtual machines, microservices. These are particularly good CPUs for microservices, tons of Docker containers, small VMs where you've got like 2 or 4 cores per VM, like micro VMs. Good choice. These are performance cores. The P cores are roughly twice as fast per core. We'll see that in the benchmarks when we get into that in a little bit more detail. And so if you wanted to run larger VMs, like 6 or 8 or 12 cores per virtual machine, the P cores are going to make a lot more sense. Intel also has another socket that is 12 memory channels native. This one is 8 memory channels. The system is configured with 2 DIMMs per channel, so I've got 2 terabytes in this configuration. We'll talk more about it in a second. But if this isn't enough, Intel has their 6900 series, and those are available with up to 128 core Xeons. Those launched in September, so that was a little bit more recent. And there are performance and efficiency core versions of that Xeon, but the 6980P is the one that we've taken a look at, 128 cores, and that is the most monstrous and performance CPU that Intel has ever done in the history of Intel. It is a monumental multi-piece of silicon. It's an incredible, you should check out the review, it's awesome. But this is about more mainstream stuff, and actually this socket is available, well, this socket, Intel has, on their roadmap, 8 socket versions of that. But this CPU also makes a lot of sense in single socket configurations because it'll repurpose the links that are normally used for CPU to CPU communication for more PCIe lanes. So 136 PCIe lanes. And that's really the flexibility that Supermicro has gone into with their chassis. So let's talk more about chassis features before we get to the benchmarks. Gosh, I hope that explanation of how Xeon 6 works. If not, you can check out our other videos or hit me up in the forum. But basically you got 2 sockets. The big socket with 12 memory channels and the littler socket with 8 memory channels. That's what this is. And then you can pick, do I want a Xeon that's based on efficiency cores or do I want a Xeon that's based on performance cores? Because they don't have Xeons that have mixed performance and efficiency cores. You got to pick all performance cores or all efficiency cores. That's your options. And those options are available in either socket. Let's go on a chassis tour real quick. So this chassis is 2 DIMMs per channel. So there's 32 sockets here. That's DDR5 6400 for 1 DIMM or DDR5 5200 for 2 DIMM for supported. This chassis also supports a CXL. This is 330 watts per socket. And the chassis is pretty genius because it's configurable. I like configurable. I like not being locked into any particular choice. So your PCIe slot configurations, you got up to 8 PCIe 5.0 by 8 or 4 PCIe 5.0 by 16 slots with support for double width GPU accelerator cards. So if you take a look at the back here, you can have 2 double height GPUs over here, 1 here and 1 there, 4 total. You also got 2 AIOM networking slots that's compatible with OCP NIC 3.0 standards, X16 and X8, 32 DIMM slots, as I said, 330 watt CPUs for air cooling. This chassis does have full support for liquid cooling. If you want a liquid cooled configuration, talk to Supermicro. You can do, it's literally direct chip cooling, so not a problem there. If you'd rather have half height graphics cards or your accelerators are half height, you can configure this for X8 slots instead of X16, and that's no problem. You can run 8 of those in this chassis with X8 PCIe 5.0 configurations. For the front, as configured, we have 8 bays, 2.5-inch U.2, PCIe Gen 5, that's NVMe and SATA. You can do SAS, you'll need the connections for the SAS controller and extra breakout cables. You can configure it with 16 or even up to 24 if you want to do that. You'll lose some of the PCIe connectivity at the back, but you can move it to the front. And remember that, depending on what configurations you want, there's all sorts of crazy stuff popping up. It's like, oh, you can have a U.2 device that's not storage. It's like, yeah, it's just PCIe. You can get crazy with all kinds of PCIe. That's where E1 and E3 are going to take us. But this chassis is maximum flexibility because, yes, I do need actually 24 NVMe drives of storage. Okay, you can do that. Or if you want PCIe accelerators, you can do that as well. On the motherboard, you've also got an M.2 slot, an extra USB 3.0 header on the motherboard if you need more internal USB 3.0 ports, no problem. And all of the PCIe breaks out through the MCIO connectors. So the MCIO connectors are what give you the flexibility. Basically, you just connect a header on the motherboard and it goes to the slot and you're good to go. This also means that you can do bifurcation. Bifurcation is this new hot thing where you have an accelerator card that can connect to both CPUs. And so instead of 16 lanes to one CPU, you have 8 lanes to one CPU and 8 lanes to the other CPU. It's really easy when you got cables. It's just like you're a punch board operator. You can route the PCIe lanes anywhere you want. And so, ta-da, it works. Maybe I want to add my dual 100 gigabit A30X accelerator. This is one of the more wacky NVIDIA cards. So dual 100 gigabit, but it's got a GPU on it, so you can do GPU acceleration for your network workload. And guess what? That'll work just fine in here. This thing's got all the power delivery and everything you could need to do that. Configurable standard power supplies. Yep, standard hot swap. Standard 2 kilowatt power supplies. That is with the 200 volt, 208 volt, 3-phase, 220, 230 volt. And as the chassis is configured, we've also got our Broadcom standard 100 gigabit OCP3 NIC. So this has a lot of really cool things like iSCSI offload and some other really neat features. It's a Broadcom chipset. Very well supported on Linux, Windows, whatever operating system you want to run. This motherboard also supports dual M.2 with a toolless release. And I thought of everything, including GPU support brackets. Our U.2 hot swap is also toolless. And adding our Kioxia CM7 U.2 could not be easier. That's it. That's all we have to do to get our U.2 mounted, and it's not a problem. Now, our CM7, these are PCIe Gen 5 drives. These are some of the fastest drives that I've tested in any server or any configuration. And so running Linux, MD RAID, 4, 8 drives, whatever you want to do, is not a problem in this configuration because you've got all the PCIe connectivity. Intel systems are really, really good for this kind of thing. The system also supports VROC. You do have to get the optional VROC RAID key if you want to use VROC RAID. VROC RAID, the performance between Intel MD and VROC is very similar under Linux, but if you have the VROC RAID key, you can also mount that volume under Windows because there's full VROC support under Windows. It does work a little differently under the hood. There's a mailbox device and some other stuff that Intel has done to ensure coherency for your RAID array or anything like that. But that is fully supported on this platform. If you're going to run VMware, you can run VROC with VMware now, which is a really nice thing. And so that plus the Broadcom chipset and the offload and managing your network directly in VMware, this would make a really nice VMware platform in a way that the efficiency core based version of this would not, for sure. So if you're looking at virtualization or hyperconverged nodes, this would be worth looking at for that type of a workload. Well, let's get this thing under benchmarking and take a look at the benchmarking because the results are interesting. If we roll up our sleeves and do the benchmarks, things in terms of the benchmarks get a little interesting, especially when you consider the E-core versions of the CPUs and you consider the pricing on Intel Arc because street pricing is not that anymore. In terms of performance per watt, this breaks even or beats Intel's own 6980p. The 6980p was almost twice as efficient versus Intel's own prior generation in terms of power consumption. Yeah, they use more power overall, but 128 cores versus 64. These CPUs are actually 2.1 times as power efficient on average for the workloads that I tested versus the dual socket Xeon Platinum comparison system that I tested against. So that's pretty impressive given that these are 86 core CPUs. We know that NVIDIA has favored this system, this type of system for this system configuration for both MGX and HGX for their own systems. In fact, these Intel CPUs are already qualified for those systems because CPU connectivity for the GPUs is important. A lower end CPU like the 6737P, which is just 32 cores, can support 4 GPUs and 3 NICs in a 2 CPU chassis, and that meets the MGX qualification. Those are the type of systems that NVIDIA was qualifying on this socket. So let's take a closer look at our benchmarks, just bearing in mind that I'm also testing 128 cores on the EPYC side and 128 cores on the Xeon side. Benchmarks, I got it set at my desk. All right, so the first thing we talk about is Intel's Memory Latency Checker, MLC. This is a really super handy utility that I use basically across every single platform that I work with, and it gives you an accurate picture of how your workload is going to behave if you're really familiar with how your workload accesses memory. Near NUMA nodes, far NUMA nodes, etc., etc. Oh, I also have the MLC numbers with the CXL device as well if you're interested in that, because it adds another NUMA node, a 5th NUMA node through a PCIe slot. What is this wild black magic? Smart Modular, they're shipping now. It's like fully qualified, fully tested. That thread on the forum will give you an idea of how these types of CXL devices work and how it can affect your memory latency and that sort of thing, especially like your raw throughput performance if you're looking at that. Now, our base system is configured with 4 NUMA nodes, and even though it's a 2-processor system, well, I mean, that 5th NUMA node with the CXL device, 4 NUMA nodes, 2 NUMA nodes per socket gives you a good balance of latency and throughput, because the memory channels that are close to the CPU are treated differently than the ones that are farther away from the CPU because of the speed of light. Speed of light is getting to be a real problem in microprocessor design. I wonder if Richard Feynman would say that there's still plenty of room at the bottom. There's much less room at the bottom than there was previously, but I digress. Depending on your workload, it may make sense to have just 1 NUMA node per socket, even if the aggregate latency is going to be a little bit higher, your average latency. MLC has stuff in there that you can sort of glean, okay, I can deal with this latency, or maybe the higher throughput makes more sense. Cache-to-cache transfer latency can give you some ideas about this, because it'll show the node-to-node latency for the near and far NUMA sockets. There's a lot of words for me to basically say, this is really good for this platform. Keep in mind, this is 2 DIMMs per channel, so it's running at the slower 5200. If you were on a 1 DIMM per channel configuration, this would be more like 6400, which is significantly faster than 5200. But having 2 DIMMs that you can keep busy in each rank makes up somewhat for the speed. So depending on what you're doing, capacity here, I mean, this is 2 terabytes in the system, which is pretty darn nice. And overall, the whole platform performance here is very good. Historically, Intel has done very well with their memory tuning for basically every workload. There's not a lot of corner cases, and looking at the MLC output here, I see that, yes, this is top-notch performance for this platform on memory throughput and latency. It's very nice to see. So let's dive into the actual particular benchmarks, because they get really interesting. Now here's a bit of a disclaimer to keep in mind as we go through the benchmarks. There's a lot of systems in here. AMD does not directly have a CPU that really addresses this middle configuration here. It's 8 memory channels, and yeah, you could run an AMD, Turin or Genoa processor that's designed for 12 memory channels with just 8 memory channels. There are certainly motherboards out there that do that, and we've done videos on that, but those are really 12 memory channel platforms. You still are buying a 12 memory channel CPU, and this is 86 cores. So, core for core, it's hard to do the comparison. So I've got some 64 core and 128 core processors from AMD that we'll use in the comparison. And I've also got some older processors from Intel. Now, really interestingly, I've also got the 6780E and the 6766E processors. These are the E-core versions of these Xeons that launched about 9 months ago. And you'll see in some of the benchmarks that it's like 2 to 1. The P cores will perform twice as well as the E cores, and you'll also understand a little bit more about what I meant about my virtual machine comment, where it's like, hey, smaller VM configurations work better with the E core Xeons, but if you've got larger or more complicated virtual machines, those P cores really are in a class of their own. For a timed Linux kernel compilation, turned in a respectable about 25 seconds. I was doing some different system configurations with the NUMA nodes for the 2P and the 2P4 NUMA node, which made a minor difference, not as much of a difference as I thought that it might make in these configurations, but for the compile benchmarks, it's basically the same. And these are turning in significantly better score than their previous flagship processors. And of course, the 6980p 2-processor Intel configuration, that's the best Intel score on this whole chart, because yeah, it's dual 128 cores versus dual 86 cores. We also test compiling with other stuff like FFmpeg, the Godot engine, Node.js, Gem5, and LLVM. And for a dual 86-core configuration, these processors are performing about where I would expect. We also like to take a look at cryptographic functions. So we also cover OpenSSL with a couple of different algorithmic configurations, RSA 4096, SHA 256, and SHA 512. And the performance here is pretty good. If you look at OpenSSL RSA 4096, I mean, your performance per core is significantly better with the 6787 versus the 6766E. I mean, those P cores are really murdering everything because RSA 4096 is kind of complicated. It's optimized. The E cores don't have as many facilities for doing this kind of stuff. And it's like, oh, clearly if you're working with OpenSSL, you should work with a P-core based solution and not an E-core based solution, or, you know, and AMD's doing really, really well here as well. But if you come down to SHA 256, well, look at that. The 6780 and the 6766E is doing amazing with SHA 256, and that's just because it's more cores. More cores is more better. So you really have to know your workload if you choose a P-core or an E-core. But keep in mind that 9755 EPYC, that's also a 128-core processor. Of course, I do also have the 9575F in there, which is a 64-core processor, but it's the frequency-optimized 64-core processor, which is a little more expensive. But also the AMD EPYC 9575F, I mean, that's a 2-processor, but it's 64 cores per processor. Now, pricing on the 9575F is really strange. At the time that I'm doing this video, at CDW, it's $25,000, but on Newegg, it's only $8,000. For database testing, we covered a number of database applications, RocksDB, SpeedDB, some mixed workloads with SpeedDB, random read, and read while writing. And the performance here for dual 86 cores is right in line with what I'd expect. This is really good performance for just 2 times 86 cores. But again, we can see AMD kind of pulling ahead here, even with their 64-core offering. Where things take a turn in that context is when we have mixed reading while writing. Reading while writing seems to be a competitive advantage for Intel, but part of this may be down to system configuration, because depending on how your 9755 is configured, you can have worse or better performance. So that's why I've got the 9755 system on here a couple of different times with a couple of different configurations. And the performance gap here really goes to show that as a system administrator or somebody that worries about these kinds of things, you really need to understand the nuts and bolts of your workload in order to understand what's going on. Whereas on the Intel platform, it seems not to really matter too much. It just, you know, seems to do the right thing. The 2P configuration on the 6787 is a hair faster, so you can handicap yourself a little bit, but you can't handicap yourself, you know, 50% as we see with the 9755 result in the SpeedDB read while writing test result. SecureMark TLS also posts an impressive result for the Intel family. AMD does pull a bit ahead here, but the performance per core is really similar to that of the 6980P as well. Now, Blender and rendering benchmarks on this CPU is really, really interesting. And also, maybe I should have given the E-core CPUs a little bit more credit for these rendering workloads, because with Blender, like the BMW 27 performance result, the 6780E, you know, 9 seconds, the 6980P, 6.45 seconds. The performance between the 6780E and the 6787P, for P cores versus E cores, is almost identical. But keep in mind that you've got basically a 2-to-1 ratio of E cores to P cores in the E core Xeon part. And that holds true for pretty much all of the Blender benchmarks. You know, the Barcelona Barbershop, everything is almost a 2-to-1 ratio. So 2 E-cores in rendering, because rendering is something that scales really well to multiple E-cores. And this kind of makes sense with also the virtual machine stuff that I was saying. So if you have a bunch of small virtual machines that don't communicate with each other, they're all isolated. Yeah, the E-core Xeons can make sense. But if you have larger VMs, you need 8, 12, 16 virtual cores per virtual machine. The P-core based Xeons are going to make a lot more sense, and you get double the performance per P-core. And that bleeds through. You can see that clearly in the rendering benchmarks. OSP RAID rendering, the way that it does the benchmarking, it's like, oh, the P-cores are twice as good, but you have half as many of them. So, you know, the items per second is 49 versus 21 on the Intel platform versus 74 on the 6980P. So the P-core performance is doing a little better on the P-core configuration versus the E-core configuration, because this is a renderer that does not scale quite as well as what Blender was doing, or Blender's doing something a little different than what this benchmark is doing in terms of the things that are available. And don't forget, you have accelerators like AMX that are available to help accelerate these kinds of workloads. Even renderers like Embry, the P-cores and the E-cores perform really similarly, but the P-cores pull a little ahead. Intel's Open Image Denoiser is also worth a look, because this depends on single core performance more than anything, and so that's why the 9755 and 9654 CPUs post worse results than like the 128 core basically will post a worse result than the 64 core. The 9575F with its insane frequency, pulls ahead, but the 6980p is super optimized for this image denoising algorithm, and so that's the best CPU on the chart. So things that are heavily optimized for the facilities that Intel offers, Intel kind of pulls ahead, but the 6787P is still behind the 9575F with its monstrous, 5 gigahertz frequency, but it's close. It's pretty close, and it's only, dual 86 cores, although the other, is dual 64 cores or dual 128 cores. So this is the first round of benchmarks. There may be more room for optimization, but yeah, I don't know. I mean, you saw the pricing slide from Intel, and that's what I'm sort of perplexed about, is that like in the channel, you can actually get these processors a lot cheaper than the pricing slide. And it may be a situation like the whole CDW pricing versus AMD pricing. Like if you just go to Newegg and you look for EPYC CPUs and you look at competitive EPYC CPUs for these configurations, then it's a little problematic for Intel, it looks to me like, from the pricing. But there are features on the Intel platform that only Intel have, things like QAT and the in-memory analytics and other accelerators. VRock, and VRock is a platform for VMware NVMe RAID. Intel's your only option if you want natively supported NVMe RAID inside of VMware, and that will be faster than any controller-based NVMe solution that you have. It's also true that single socket versions, like you can get a 6700 single socket 8700, and that is 136 PCIe lanes, because they repurpose the CPU interconnect and use those for PCIe lanes as well. So you can get a single socket server based around these CPUs that have 136 rather than 128 PCIe lanes. And that is sort of a competitive differentiator. With this memory, with this platform being designed for 8 memory channels instead of 12 memory channels, and the performance that goes with that, I mean, maybe in terms of like the total cost of the system, there's something there, but Intel's going to have to get really, really aggressive with their pricing to stay competitive in this market. And yet, Supermicro's pricing on this system for other comparable systems for this performance level seems pretty solid. So Supermicro must be getting some kind of a discount on this versus the street price on the Intel slide there. I don't know what to make of that. The market will tell, but this is what I've been able to glean in terms of raw performance. So these are the benchmarks, and like I say, check out the link. There's a lot more that I didn't go over, but yeah, it's interesting. Comment below. Yeah, benchmarks. I mentioned CXL. I've got a separate video coming on this awesome device from Smart Modular Technologies. This is the CXA4F1W, and this is an easy way to add another 512 gigabytes of memory. Well, this is the 4 memory channel version. I should be taking a look at the 4 and the 8 DIMM version, but the CXL expander gives you a memory-only NUMA node, or on a platform like the Intel platform, you can configure it so that it is in flat memory mode, so the system just manages it for you. We know from Intel's own Flat2LM instance testing that they did for the launch of this that there was only a 3% degradation in that AI workload type performance. And that was with using CXL memory as opposed to system memory. So this system configured with 2 terabytes, so 2 terabytes wouldn't get it done. Yes, the platform supports 4 terabytes, but that's exponentially more expensive than 2 terabytes. Would another 512 gigabytes get it done? Maybe. That is the case for some of these AI workloads. And so I was curious to take a look at this, and well, long story short, we've been testing llama.cpp on the forum, and we've also been using high-speed storage and trying to do memory mapped I/O. None of the high-speed storage stuff really works correctly, that's been a whole other benchmarking adventure. Not just on this platform, but other platforms as well. But CXL works fine. And so CXL is basically very nearly plug and play, at least if you're running Linux, you got some configuration to do. And so if you're running a system like this that has 2 terabytes of memory natively, you can easily run the 700 gigabyte DeepSeek R1 model, as I was saying a few moments ago. Just from memory, and 10 tokens per second is sort of the floor. It's achievable, and you can even do better than that with some tuning and optimization, because nobody ever figured you'd be running that kind of thing from a system. And if you've got a smaller GPU, like a 48 gig GPU, you can do some of the input processing on that. Right now, AMX extensions are not doing much for us with llama.cpp, but this is also frontier engineering. We'll probably get there. There will probably be optimizations. Certainly Intel's own slides show that in some AI scenarios, AMX is going to help tremendously. So this platform itself supports CXL 2.0 with support for all type 1, 2, and 3 devices, and backwards compatibility for CXL 1.1. And that was very nice to see and actually be able to test it. So thanks, Smart Modular. CXL memory type 3 tiering support for both capacity and bandwidth expansion is also supported by Intel on the platform, which is amazing. So good job, Intel, doing all of the work to do that. And, there is some support for managed hot plug and device addition and removal. So those are the things that you'll want to talk to about with Supermicro, though, if you're planning to go that route, so that you can get a fully qualified solution. But I'm delighted that CXL works as well as it does on this kind of stuff. But for me, this is all about the frontier. The frontier experience with CXL. It is nice to see more coherent CXL support out of the box in market products and server configurations and that sort of thing. Coherence, pun intended. Bottom line, these benchmarks show that Intel is in a much stronger position than many people give them credit for. Our own experiments with DeepSeek and running huge AI models that would otherwise be impossible to run unless you've got nearly a terabyte of VRAM in which to run it, can run fine on CPUs, just like these CPUs. These CPUs exactly, actually. The full model, not a distilled version, to be clear. Not cut down in any way, 700 gigabytes. Now, with quantization and sparsification and the AMX extensions, there's a lot of promise here for even better performance, better than what we're seeing from a pure CPU workload. I mean, you can get 10 tokens per second. When you are ready to multiply the cost of the system by like 10x, then you can add PCIe accelerators, GPUs, whatever, AI accelerators, whatever you want to call them these days. And if you choose NVIDIA, Supermicro's platform is qualified. Supermicro's shipping many of those systems. But also the AMD Instinct line, again, Supermicro. And even Intel's Gaudi 3, again, Supermicro. Just whichever way you want to go, you got PCIe 5 lanes in order to do it. But if you just want to do some experiments, this thing will hold 4 to 8 GPUs, depending on what the physical configuration is. So this has been a quick rundown of the Intel Xeon launch and the Supermicro 222H-TN and the benchmark results from that. If you want to see me run another workload on these CPUs or on this system, let me know. Let me know quick, because I've got to get this system off to where it actually goes. So yeah, 2 terabytes of RAM is not just going to hang around the office for forever, because, oh my gosh, 2 terabytes of RAM and 86 cores, and it's got the performance. I've also got the video coming with more details on how we're faring with this Smart Modular CXL device. Yeah, this is 512 gigabytes of DDR5 memory on this PCIe card, and we're going to use this on this platform as well as the AMD platform. So get subscribed and engage for that, because this is a cost-effective way to add a lot more RAM to the system, as we saw from Intel's own slides at the launch of the 6980p CPUs. What an amazing and interesting future we live in. I'm Wendell, this is Level 1. If you have any questions or if I missed anything, let me know in the forum, hit me up, let's do some videos, whatever. I'm signing out, and you can find me there.